Hello everyone, I am Tania Allard and this is my presentation for PyCon 2020 online. I'm going to be talking about Docker and Python and how we can make them play nicely and securely for data science and machine learning. I am a developer advocate at Microsoft and my role is helping other developers and professionals, researchers and academics to do their work better. This can be by creating new applications or developing content for them and working with our engineering teams. You can find me on Twitter at Ishak or GitHub, and on my website is trailer.dev. Also, you'll be able to access these slides on this website, and the link is going to be accessible on all of the slides, so you can refer to them whenever you want. So let's start with what you're learning today. First, we're going to learn why you want to use Docker, what are the advantages of them, and the specifics of some Docker problems when working with data science and machine learning. I'm also going to give you some tips around security and performance when you're working with Docker and containers in general. Some tips on how not to reinvent the wheel, but to automate. And finally, I'll provide you some useful and practical tips on how to use Docker for your data science projects. So let's start with why Docker? Why you might want to use Docker for data science or for anything. More than likely, you're developing your applications or your models or your scientific projects in your local computer. So you might be familiar with this kind of development where you create your application, whatever it is. I'm just going to generalize here. And then you want to ship this to somebody else, whether it's a customer or a colleague. And how many times have you encountered this issue where it says that module doesn't exist? And that's probably the least of your problems. What about folks using different runtimes? Maybe someone is still using Python 2, and you developed your whole algorithm and your whole model using Python 3. Or what about you developing your applications on Ubuntu, and somebody else was using Red Hat, or was using Debian, or Windows? How are people going to know what dependencies they need, or what environment they need, or configuration files if you're not explicit about it? And here's where Docker comes into play. Docker is a tool that allows you to create, deploy, and run your applications or projects by using containers. And throughout the presentation, I'm going to be using that little icon to represent a container. But how do containers help you? Well, the most obvious answer for this is that they provide you with a solution to the problem on how you can get your software or your models or your applications from when you're moving from one computing environment to another. This can be going from your laptop to your test, staging, or production environment, or it can be your laptop and somebody else's laptop. So in a world where you're using containers to do your development or data science world, this is how your workflow would look like. You develop your application, but in this case, you're also adding the libraries, all the dependencies, the runtime environment, and the configuration files that you need for it to work. So you build your container with your application and all of these extra assets. So when anyone wants to install this or run this in their machine, it's actually doable. So I can imagine that those of you that are familiar with virtual machines might think that it looks or sounds a bit familiar. Well, the way Docker and containers work is that you would have your infrastructure, probably a server or the cloud or your computer, and your host operating system. And sitting on top of that, you'll have Docker, and then you can have a lot of different apps that are containerized running within this setup. In this scenario, each app is containerized, so Docker and containers work at the app level. Each app runs as an isolated process. The whole of operating system and the infrastructure are abstracted away. So it doesn't matter if you developed on Ubuntu or Red Hat and somebody else is using Windows. Virtual machines, on the other hand, will start also with your infrastructure, but it will have the hypervisor sitting on top of that. So your hypervisor will be sitting on top of your physical server and will have two whole different operating systems running on top of that. So the abstraction works at a hardware level, meaning that you're going to have not only your app, but the whole operating system, binaries, dependencies, and everything working on top of your infrastructure. When you delve into the world of Docker, you're probably going to also use or hear the words image and container. And these two terms can seem a bit confusing at the beginning. So let's start debunking. An image is an archive with all the data needed to run the app. And as an archive, it needs to have a tag attached. It can be latest or it can be a concrete tag, whether using semantic versioning or calendar versioning or a reference of the commit if you're using version control to decide what the tag is going to look like. When you pull that image from a repository, probably Docker Hub or your private repository, and use the command docker run, then that Docker image actually creates a container where you can do your development work. And all of your work is going to be in this isolated container. So what are some of the common pain points when using data science, machine learning, and Docker together? First of all, we tend to use complex setups or dependencies. And this is just because of the nature of Python, some packages, and some libraries. We also have a high reliance on data and databases. A common characteristic of data science and machine learning projects is also that they tend to be very fast evolving projects. During the phase of research and development, we tend to do a very fast and iterative process. And as you go deeper into Docker, you're going to find that it's actually quite complex, and it might take quite a lot of time to upskill and learn everything you need about it. Also, a common concern is whether containers are secure enough for our data or our model or algorithm. What happens when you're working with healthcare data, or criminal data, or financial, or any other sort of data that could help to easily identify individuals? So let's dive into scenarios, tips, and best practices for Docker for data science and machine learning. Some of these are going to be specific for our use case. Some others are generally applicable. So if you're not a data scientist or a machine learner, but rather a software engineer or a DevOps folk, you can also learn and apply some of these tricks. Okay. Also, so we've already learned what are some of the main problems or some of the complexities that we might encounter when we are using Docker or just working in data science. So how is actually creating containers for data science projects different from web apps? One of the first things that I mentioned is that we can have very complex setups and dependencies and installations. A lot of folks have been discussing this very openly in our Python community, because this is not a problem completely inherent to our data science or scientific computing ecosystem. The trick to overcome this is finding a robust, reproducible way of working. You might feel tempted to try all of the newest tools and have a very complex environment, but sometimes just choosing the right tool, adhering to best practices, can take you a very long way. Now, when we're working in data science and machine learning, not every deliverable is an app. Not all of the things that we develop as part of machine learning workflows can be productized as an app. Also, not everything is model. Not everything is going to be delivered as a model that can be accessed through an endpoint or an URL, or is going to be on a smartphone. We heavily rely on data. Data is one of our most valuable assets. And we'll also have a mixture of wheels and compiled packages. A lot of the Python scientific ecosystem packages actually rely on compiling the binaries. When you're working with sensitive data, we also need to make sure that we have the right security access levels for both data and software. And we're also going to have a mixture of stakeholders: data scientists, software engineers, machine learning engineers. If you're working on creating an app that uses machine learning in the backend, you're also going to need someone taking care of the front end and mobile development. So this increases the complexity of your projects. And each of these stakeholders have different requirements and different needs. Let's dive into the basics. If you've never used Docker images, this is going to help you to better understand the workflow. If you've used Docker before, this is going to serve as a refresher. The way we work with Docker and create containers and images is by specifying all of the instructions and requirements through Docker files. On the right-hand side, you have a not very good example. Well, a bad example on how to build a Docker file, but it should be simple enough for you to understand how we can structure this. We normally start from a base image. That is, let's say, our building blocks. When you're using Lego blocks, you need a solid foundation. Then you're going to have a set of instructions, and this is where you actually install all your packages, all your dependencies, compile binaries, and move files from your local development environment into your container. And finally, you have an entry command. This can be either to run an interactive application like Jupyter Lab, or executing a script, or simply to access the command line. Something that you have to be aware is that each of the instructions that you contain in your Docker file creates a layer. So the closest analogy for you to think about Docker images of is to imagine an onion. Your base image is going to be at the core. And every time you run an instruction using the command run, it's going to generate a layer, which is going to be wrapping the previous layer. So everything is self-contained. The more instructions you have, the bigger your onion or your container and the number of layers. So you have to be very smart about how you are creating those layers. One of the crucial parts when building containers is selecting the best base image. You're going to read in a lot of places that Alpine Linux is the best distribution because it's very lightweight and you can build your containers quite easily. So I would like to give you a word of caution. To start with, if you're going to be building all your images from scratch, make sure to use official Python images. You can find them all in those links and find the different versions and tags. Now, going back into the question of Alpine Linux, it is a very lightweight base image, which means that you're going to have to spend a lot of time building libraries and dependencies, and it's not worth the complexity. If you're looking for Python 3.8, I recommend you using Slim Buster. It is based in Debian, and it also has the long-term support at the moment, so it's very likely to have continuous security updates over the next couple of years. If you're going for Python 3.7, I recommend going for Slim Stretch or Slim Buster. Slim images have the full distribution, but they only remove unnecessary files like manual pages. Creating a Docker image from scratch can take a very long time. So if you find that you're going to be needing Conda, Jupyter Notebooks, and in general the scientific Python ecosystem, which is more than likely to occur for data science and machine learning, use the Jupyter Docker stacks. The Jupyter community has put already a lot of effort in building these containers and images. They all start from an Ubuntu-based image, and they layer one on top of each other. So if you only need the Jupyter Notebook and you want to install your dependencies yourself, you can build from there. If you need more complex setups with scientific Python programs as well as TensorFlow, there is something for you. You can also use PySpark or a data science notebook that also contains R. And I think there is also some other community stacks that allow you to use Julia. You can also use those as base images to build your Docker images. So, with further ado, let's go into some of the best practices for you to get started. First of all, always know what you're expecting. And this goes without saying. Always make sure that you're using a concrete tag. So in the directive from, always use a specific tag. For example, base notebook C.03. Avoid using latest because more than likely when the next push is created or the next image is created, that's going to change your base. Provide context with labels. This is very important. You can add important information like who's the maintainer, which is a security context, if it's meant to be used in production, and many others. Sometimes we might feel the need to have very complex run statements, but legibility is extremely important. Make sure to split run statements and sort them. And also, prefer copy, the command copy to add files, whether that is to copy packages, configuration files, or something else. You'll see that also there exists an add command, but copy is more straightforward and it's also very explicit. Also, Docker is very good at using cache. That means that if you have a dependency or something that has not changed within your layers, then it preserves that layer to speed up your build without needing to download dependencies or compile them or just install them on the fly. Since every instruction creates a layer, whenever any of these files contained within these instructions is modified, the subsequent layers have to be built. So be very careful when you're restructuring your Docker file. Separate instructions per scope. Make sure that you're actually using the cache to its maximum. And also only install necessary packages. Sometimes we might feel the need to have, additional packages just in case we end up needing it. But that is going to bloat your image significantly and also increase the potential risks, the potential security, and the image size overall. And also explicitly ignore files. If you're familiar with Git for version control, you can create an analog file. Not only it will help you to avoid carrying unnecessary files like your README or some data. Always try to avoid adding data. Especially when we're working in data science, we don't want to hard code the data within our container, but we want to access probably data from a database or even from our drive. Also, make sure to never expose secrets. Explicitly marking files with secrets in our Docker ignore will ensure that they are not within your layers. I've already told you not to add data to your Docker files. So there are two ways, or there are multiple ways in which you can do this. One is you can access a database and ensure that your container has access to whatever port your database is accessed through. If you have your data locally, or for example in your cloud virtual environment, you can use bind mounts to directories, or just specify which directory your data or your files are and mount them into your container. That way you can run your container, you can start up your container, do your development work, and the progress or the changes will be saved directly in your local files. Also, there's a big culprit there. You also need to ensure that you're running as a non-root user, because you might have problems accessing files or changing the permissions of the files. I'm going to dive into this a bit deeper when we come to security. So thus far, I've only given you some good practices on how to start building your Docker containers. These are going to take you a very long way. One of the major concerns about using Docker and containers relies on security. I have mentioned before that you have to use a user flag when running your containers. And this is mostly to minimize privilege. We call this favor the least privileged user. This is very important to minimize or prevent attacks. First, run as non-root user. By default, Docker runs as root. And this is because you need to normally update libraries within your kernel. So whenever you need to do any installs, you're able to do apt-get because you are a root user. Also, make sure to minimize the capabilities of your user. For example, on your Docker file, for example, in this Docker file example that you have on the slide, you're explicitly creating a user named Jovian. If you're using any of the Jupyter Stack containers, you don't have to worry about it, because the folks from Jupyter have already spent a lot of time making sure that you're not running as a privileged user. However, if you're extending any of their Docker containers, you need to make sure that you also add an unprivileged user, change the root to do any system updates, and then turn back to your non-privileged user. Be very careful when working with sensitive information. Sometimes it's very easy to have environment variables that correspond to passwords or keys or API tokens. The first entry point to secure your containers is adding the files that contain those keys to your Docker ignore, so they don't get in there. Try to keep all of this out of your Docker file. You can set runtime environments that can then be provided by flags or other context. Sometimes we can feel that if we copy those files into our container within a layer and then delete it, then because we're building on top of that, that's not going to persist. But because of the Onion organization with their containers, even things that we've moved and deleted in previous layers are cached, so people can access them. A very powerful way to secure your Docker containers and to keep your secrets secret is using multi-stage build. If you fetch and manage secrets in an intermediate layer, that layer or that image is disposed, and then they're not persisted in the final image. Another advantage, and that is very, very important and helpful, especially in the scientific Python ecosystem, is Because not all of our dependencies will have been packed as wheels, you might need a compiler. Whether it's a GCC or a J-Fortran compiler. So it's very helpful to have those compilers compile the binaries in an initial image and then just install or copy across the compiled packages. And in general, when you're using multi-stage builds, it helps you to create smaller images. Because you can get rid of all the unnecessary and unwanted files and then just keep what you really need. On this Docker file that I have as an example, we're starting our image from Python 3.8.2. And we're calling it compile image because that's where we're actually doing some system updates, installing our compilers, creating a virtual environment, and compiling our dependencies. So when we do Docker build, whatever our image is and provide a context, Docker will start building that compile image. Once that's completed, it's going to move on to the runtime image. And in this runtime image, what we're going to do is copy only the virtual environment, or you can copy only some of the compiled packages. This way, you're getting rid of the compilers and any other secondary files that you don't need. And your final image is going to be the runtime image, but with the tag that you provided when you call the command docker build. The final part of this talk refers to automation. So far, I've given you a lot of tips and a lot of ways to increase the performance, reduce the image, ensure that your image is secure. But it all can be very, very daunting, especially if you're only building containers for your personal use and for reproducibility. One of the main advantages of using Docker containers is reproducibility. We care a lot about this when we're doing machine learning, research, and scientific computing. We usually want to share our assets with others, or we want to deposit our data, code, and papers so that folks can verify our research and our findings. So one of the best things that we can do is try and automate. Whenever I talk about reproducibility, or whenever I talk about reproducibility in the context of machine learning and scientific computing, something that I always recommend everyone is to have a standard template. That way, everything lives within a specific space, and you always know what you're expecting again in terms of your folder structure, what files should be, and you have explicit conventions about your directories and naming. If you're looking for good project templates for data science projects, try to use a cookie cutter for data science. If you're interested in the Docker version of it, use cookie cutter Docker Science. When you use these packages, it's going to create a robust template for you to start your data science project from. You will see in the image the layout of the cookie cutter Docker Science. So we have the configuration for Jupyter, we have a Docker file, we have our directory for our models and requirements and additional scripts. So this is by default enabling you to use Jupyter notebooks. In a similar way, the project Jupyter Docker stacks, they're all enabled with Jupyter notebooks. So whenever you run your Docker container using any of their images, the first thing that you have is access to the terminal and to your Jupyter notebook, so you have a reliable and well-known environment. The second step is do not reinvent the wheel. Sometimes we might feel the need to start everything from scratch. There are very good packages that the community has already been working on. One of my favorite packages is repo2docker, where it will take a repository, it can be either local or through an URL, and the main advantage is that it's already configured and optimized for data science and scientific computing. The common workflow is that you're going to have a configuration file to explicitly describe the requirements that your project relies on. Once you have that, you execute the command Jupyter repo to Docker and provide a path. It can either be a local directory, or it can be a URL corresponding to a repository, or a DOI from Zenodo. It will then use some of the Jupyter Stacks Docker bases and build your Docker container. The most neat thing about this is that you don't even have to write a Docker file. You don't have to spend a lot of time refining your Docker file and learning how to go about it. So if you're looking for a reliable way to create Docker containers, repo to Docker is your tool. Whatever you're using to manage your dependencies and your environments, whether it's contab, pipenv, pip tools, even if you're working in R or Julia, you can use that to create your container. And bonus points, because those containers are of the same format that the ones used for Binder. So if you're looking at sharing your assets in a reproducible and interactive manner with minimal overhead for others, Binder and repo to Docker are your tools to go. And finally, delegate your continuous integration. So far, I've mentioned that you can create your images and tag them. There are a lot of instances where you want to create a new Docker image or a new version. Probably you created a release of your package or your model or your app. So you create a tag in your version control system and you want an accompanying Docker image to make sure that everything is up to date. But a very good practice is also to rebuild your images frequently or often. If you are extensively using Docker for research and development, testing and production, probably weekly is a good idea. That way you ensure that you're getting all the security updates released. But it can be cumbersome if you do this by hand. So the best way to go about it is using continuous integration. Whatever tools you are using already, whether Travis, GitHub Actions, or anything else. And delegate your build. That will allow you to take less care of the building and pushing of your images and focus more on your code. I've added an example here for a workflow for GitHub Actions. For me, I have two triggers. One is whenever I create a new tag, and also I'm specifying that my image is going to be built every week on Sundays at 2 o'clock in the morning. But you can choose any time of the day. Because GitHub Actions allow you to keep all your secrets, all your keys as secrets, you don't have to worry about your Docker username or password to be exposed. And because it also integrates natively with your version control system, you can tag directly using the ref that can be, for example, a tag. And because it integrates nicely and directly with GitHub Actions and your version control system, you can directly tag your Docker images either using a tag reference or the SHA or any other reference from GitHub. So you can use details from the branch that is coming, the date, and so on. So in this workflow, or in a same workflow, you would want to have your code in version control. This includes, for example, all your scripts, your specification files, whether it's an environment.yaml file, or a pip file, requirements, or any of the such. And then you can specify the triggers as a tag and the schedule trigger. So whenever any of these two events, whether it's Sunday at 2 a.m. or you created a tag, that's going to trigger your continuous integration. which is going to build your image. And then it's going to push your image to the repository. So you don't have to worry about your code and your images getting out of sync. So to summarize, let me give you the top tips for you to work with Docker and data science. First, rebuild your images frequently. Make sure that if you're going to be using your containers, that you are constantly rebuilding it. That ensures that you get security updates and that also things are not broken. Never work as root. Minimize the privileges. The lower privileges you have, the better. Also, keep track of all the ports that you are using and how you're binding them to your container. You don't want to use Alpine Linux. Go for Buster, Stretch, or the Jupyter stack. Always know what you're expecting. Pin your versions, everything. Pin your image. Use a commit identifier to tag your images. Bonus point if you're using pip tools, Conda, Poetry, or pipenv to manage your environment and dependencies. Leverage the build cache. This can significantly affect the performance and as well as the security of your image. Sometimes we feel like we have to reuse the same Docker file for all of our projects. Eventually, you're gonna realize that you end up with a super big image with a lot of dependencies that you really don't use. So make sure to use one Docker file per project. You can have a base image, for example, parting from the base notebook from Jupyter Stack and build from there. Use multi-stage builds. If you are going for the option of creating your own containers from scratch, consider this. If you need to compile code or you need to reduce your image size, this might be a good option. Also, make sure that your images are identifiable, that you can identify whether they're meant to go in test, production, or research and development. Be careful when accessing your databases and using environment variables, as well as build variables. Do not reinvent the wheel. If you don't need really complex setups or very specific packages or configurations, use repo to Docker. Or use the Jupyter ecosystem stacks to get you started. You don't have to do everything from scratch. And you also don't have to do stuff manually. Try to automate. If you're already using GitHub, try to explore GitHub Actions. If you're using GitLab, it also has an incredible CI and CD integration. Try to leverage them. And finally, use a linter. I didn't dive into this before, but it can go a very long way when you're building your Docker files, so you can identify errors early on. Depending on the editor that you're using, there are some really good linters out there. VS Code has an excellent Docker extension. It can help with image inspection, building, linting, adding support for Docker files, and syntax highlighting. If you follow some of these top tips, I can guarantee your workflow and your images are going to be working much more nicely with machine learning, Python, and data science. I am sure you can benefit from a lot of this. Take and use whatever you need. Automate wisely and reuse wisely as well. I hope you have enjoyed this talk, and thank you very much for your attention. If you need to reach out or have any questions, these are the means in which you can contact me. Keep enjoying PyCon Online. Bye.